String theory. String theory has had a profound impact in the mathematical development of the mathematics. I indicate how string theory can be considered as a two-parameter deformation of classical geometry, where one parameter controls the generalization from point to loops and the other parameter controls the quantization in terms of the sum over topologies of Riemann surfaces. The final mathematical formulation of non-perturbative string theory, which is not yet there, will have to bring together geometry, non-commutative algebra, and loop surfaces. Introduction. Over the year, string theory has been able to enrich various fields of mathematics. Subjects like algebraic and differential geometry, topology, representation theory, infinite dimensional analysis, and many others have been stimulated by new concepts such as mirror symmetry, quantum cohomology, and conformal field theory. In fact, one can argue that this stimulating influence in mathematics will be a lasting and rewarding impact of string theory in science, whatever its final role in fundamental physics. String theory seems to be the most complex and richest mathematical objects that has so far appeared in physics, and the inspiring dialogue between mathematics and physics that it has treasured in blooming and spreading in wider and wider circles of mathematics. Physics and mathematics. This synergy between physics and mathematics is definitely not a new phenomenon. Mathematics has a long history of drawing inspiration from the physical sciences. Going back to astrology, architecture, and land measurements in Babylonian and Egyptian times. Certainly, this reached a high point in the 16th and 17th centuries with the development of what we now call classical mechanics. One of its leading architects, Galileo, has given us the famous images of the book of nature in second segregate waiting to be decoded by scientists. Philosophy is written in this grand book, the universe, which stands continually open to our gaze, but the book cannot be understood unless one first learns to comprehend the language and read the characters in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures, without which it is humanly impossible to understand a single word of it. Without these, one is wandering in a dark labyrinth. This deep respect of mathematics didn't disappear after 17th century. Again, in the beginning of the last century, we saw again a wonderful intellectual union of physics and mathematics when the great theories of general relativity and quantum mechanics were developed. In all the centers of the mathematical world, this was closely watched, and mathematicians actively participated. If anywhere, this was so in Göttingen, where Hilbert Michioki Wall, namely, and many other mathematicians made important contributions to the physics. Theoretical physics have always been fascinated by the beauty of their equations. Here we can even quote Feynman, who was certainly not known as a fine connoisseur of higher abstract mathematicians. To those who do not know mathematics, it is difficult to get across a real feeling as to the beauty, the deepest beauty of nature. If you want to learn about nature, to appreciate nature, it is necessary to understand the language that she speaks in. But then Feynman also said, if all mathematicians disappeared today, physics would be set back exactly 1 week. One mathematician's answer to the remarks was, this was the way God created the world. I am actually aware of the fact that the marriage between mathematics and physics, which was so enormously fruitful in past centuries, has recently ended in divorce. Thank you so much.